Okay, let's get started. Sorry to be so slow today. Okay, so we could either do this in two ways. We could either, tomorrow you have a test. Test is pretty important. We could either, do a review for the test and ask questions, or we could, and then do some lecture. Or we could do the other way around. We can do lecture first, and then you can ask questions later. Does anyone have any preference? It's the same thing, right? Lecture first. Okay, lecture first. Okay, so yesterday we were doing introduction to differential equations, right? And so one of the things that we one of the equations that we had was this sort of exponential growth. Exponential growth, right? So remember what that was. That was if you have some population, right? Your population at time t, right? And you made an assumption about the population that the rate of change of the population was proportional to the size of the population, right? If the rate of change of the population was proportional to the population itself, then in that case, you did your separation of variables trick. You said, okay, I'm going to write this as 1 over p, 1 over p prime equals k. Right? Divide both sides by p, and then integrate both sides with respect to time. Okay, integrate both sides with respect to time, and you remember what happened? You ended up with the natural log of p of t equaled kt plus c, which told you that p actually was some constant times e to the kt. Right. So this was the first differential equation that we did, and you see that what it predicts is that your population is just going to grow infinitely. Okay. But that's impossible, right? Because your population cannot grow infinitely, right? That's as time goes on, your population is going to reach some constraint. Okay, and so there's a more sophisticated, so for maybe a slightly better model, there's this thing called the logistic growth model. Okay. Logistic growth model, and the assumption you make there is that the derivative equals, again, it's k times the population at that time, but you throw in another factor, m minus y. Okay, where m is some constant. M is some positive constant. M is a positive constant. Okay. And so you see what happens in this case, right? The derivative is proportional to ky, but as y gets bigger and bigger, then you get closer to this. As y increases, you get closer to m, and then my becomes small, right? So think like this, right? When y is small, then this is just like kmy, right? And at the beginning, you're going to grow exponentially. Okay, so at the beginning, so here's time, and here's your population. Okay, and you grow exponentially, but as you get closer to m, your derivative becomes smaller and smaller, right? And as you get closer and closer to m, your derivative becomes smaller and smaller, right? So your slope, the slope of y, right? This thing is the slope, right? This is the slope of y. So at the beginning, the slope of y is increasing, it starts to grow pretty fast. But then as you get up here, the slope starts decreasing, right? Okay. And so this is, this is to model a world where there's some limit on the food, right? There's some limit on the total population. This m is basically like your maximum capacity, right? The most that the world can handle for this population. Okay. So we're talking about differential equations. Yesterday we had this exponential growth thing, and today we are throwing in an extra piece. Okay. So yesterday it was the rate of change is proportional to p, right? Proportional to p, and today the rate of change is proportional to p and then times some number minus p. Okay. So we want to find the solution. Right? We want to find the solution in the same way that we did last time. Okay. So what do? We start off with this ky m minus y. Right. And then we're going to do separation of variables on it, right? So we play the same thing as before. We move everything involving y to one side, and we move everything involving t to the other side. Right. And if you don't like that, you can write it like this: y prime t equals ky of t m minus y of t, and then divide both sides, y prime of t over y of t m minus y of t equals k, and then integrate both sides. So we're going to integrate both sides, and we integrate both sides over here with respect to t. Okay, so either way, if you if you don't like thinking about these infinitesimal guys, you can do it that way as well. Okay, so either way, you do the separation of variables trick, right? And then you integrate both sides, right? So on the right-hand side, of course, you're going to get kt plus c. What happens when you integrate the left-hand side? How do you integrate something like this, dy over y minus m minus y? Does anyone know? You should know, right? Maybe it doesn't look familiar because it's in y. Suppose I gave you something like this, x m minus x, and I said, please integrate this. How would you integrate this? You know how to do it. You know a technique. Right. 经常。The log will be involved, but you need to do something else first.
Xm minus x squared.
No. Does anyone know? You could do integration. You could use partial fraction decomposition. Right. This is you see that you're integrating something where you have linear terms on the bottom, right? And then so you're going to express this as, some a over x plus b n minus x. Actually, let me switch it back to y, since we wrote everything in terms of y over there. Okay, so you take this thing, 1 over y m minus y, you know it's going to be something like this, b over m minus y, right? And then you figure out what a and b are, right? So you say, okay, well, 1 is going to be a m minus y plus by, right? And then you say, okay, negative a plus b equals 0, right? If you look at the coefficient of y, negative a plus b is 0, right? And you also see that that ma equals 1, right? So a is 1 over m, and b is also 1 over m. Sri-Chan, are you okay?
Yeah.
Anyone have questions? No? Okay, all right. This is just partial fraction decomposition, right? And so what we end up with is that this equals actually 1 over m times 1 over y plus 1 over m minus y. Right? Okay, so let's go back. So let's go back to over here, and what we get is that the integral of dy, the integral of 1 over m times the integral of 1 over y plus 1 over m minus y dy equals kt plus c, right, from here. So we're integrating this guy. Let's write it right here, right? And you see what you get, right? You get 1 over m times the natural log of the absolute value of y minus the natural log of m minus y equals kt plus c. Okay. Thinking about the behavior of y, right? We know that it stays between 0 and m. Okay. So these guys are positive, and so we can get rid of the absolute values. M minus y is positive. Absolute value y itself is also positive, right? So you get natural log of y over m minus y equals m kt plus some new constant. Everyone okay up to this point? Everyone following? Anyone have questions? Okay. So, right. So again, we take we exponentiate both sides, right? So we get right, e to the natural log of y over m minus y equals e to the mkt plus c prime. That's to say that y over m minus y equals some new constant times e to the mkt. Okay. Okay. So, okay, gonna keep on going. Let's say that the initial population is called y naught. We're gonna call the initial population y naught. Okay, so what does that say? That y naught over m minus y naught equals c double prime e to the mk times 0. Right, just plug in t equals 0, right? So at t equals 0, you get this, right? C e to the mk 0 is just 1, and so that tells you what c double prime is. Right. Okay. Okay, right, so at this point, we have this formula. Oops. This equals y naught over m y naught times e to the mkt. Right. We figured out what c double prime was. So we're just going to plug in. We just put that in. Right. Remember, we're trying to figure out what y is, right? We want y. Right? We're trying to figure out what the solution looks like. So let's solve for it. Let's solve for it. Right? You say, okay, multiplying through, we get y equals y naught m minus y naught e to the mkt times m minus y. So just multiplying through by m minus y, multiplying both sides through by m minus y. Right. And you see what you get. You get let's say it like this. M y naught over m minus y naught e to the mkt minus y naught m minus y naught e to the mkt times y equals y. Okay, I'm just distributing, right? I take this times m and this times negative y. Right? This times m and this times negative y. Right? So I've got this times m and the same thing times negative 1. Okay. Then we're going to solve for y by moving this to the other side and then dividing by 1 plus this thing. Right? So let's move this thing to the other side, and we get 1 plus y naught over m minus y naught e to the mkt times y equals m times y naught over m minus y naught e to the mkt. Okay. And then we divide both sides by y. Dividing both sides by the coefficient of y. So what does that give us? So that gives us that y is this thing, right? M y naught over m minus y naught e to the mkt, right? Divided by 1 plus y naught over m minus y naught e to the mkt. Okay. We haven't really done anything. We're just doing arithmetic or algebra. Okay. So at this point we're going to do more algebra just to simplify it a little bit. So that's the answer, right? Y is this function, but let's simplify it a little bit to make it easier. So let's multiply top and bottom. So divide top and bottom by e to the mkt. And multiply top and bottom by m minus y naught. Okay, just to make it easier. Okay. So, right, the m minus y naught cancel, the mkt cancel, right? And we end up with y naught m on the top. And then on the bottom, we would end up with m minus y naught e to the negative mkt plus, right, we end up with this term plus, these guys cancel, plus y naught. So we get y, here's the last formula. So I hope you think this is pretty cool for you, right? You start off with something, you start off with an assumption. Y prime equals some constant times y times m minus y, right? This is all we started off with, right? Some assumption about the derivative. And then it turns out that the function has to look like this. This is what the function is. You cannot be if you make that assumption, then your solution is going to look like this. This is it. This is the only solution to that equation. Okay. And it describes exactly how the population will evolve. If the population follows these rules, the population is going to evolve like this. Right? And you see what happens as so observe. As t goes on to infinity, what happens? As t goes to infinity, what do you see happens? Well, what happens to this e to the negative mkt? It will turn into e to the negative mkt. So m and k are positive numbers. We're taking e to the negative, basically like e to the negative t as t goes to infinity. What happens to it? goes to 0, right? So this term is going to vanish. As t goes on to infinity, this term basically vanishes, and you end up with m. Right? So that's sort of what we saw before, that as we were thinking about it, what's going to happen is that the population is going to have this boom. At the beginning, it's going to have this boom when there's a lot of food, the population behaves as if there's no constraints and there's just exponential growth. Right? So exponential growth at the beginning, but then it starts running into the limitations of the food supply, right? And then the population is going to quickly start leveling off, and then reach some sort of stable state here. Okay. So that's what this assumption about the rate of change gives you about the population, tells you about the population. And so this is called this sort of stuff is called logistic growth. So this is maybe the hardest, the most complicated example that we'll see of separation of variables. Okay, any questions about this thing? Questions? Right. So just everything you is within your ability, right? You start off with dy dt is ky m minus y, right? You do the separation of variables. Right? You do the separation of variables, and then from here you use integration by parts. Right? This is easy to integrate. Use the partial fraction decomposition. Use the partial fraction decomposition on this, and you end up with this equation. Right? Yeah. Right. You end up with this equation by using the partial fraction decomposition. Right? And then from here, it's basically just solve for y. Right? So from here on in, it's basically solve for y. Right? And we solve for y, and it turns out, and solve for y and simplify a little bit, and it turns out to be this thing here. Okay. So it took a while to do, but every step of it was actually trivial. Every step of it was just something that you knew how to do. Now we're going to go back to 7.6. So 7.6 was all these sort of physics, applications of calculus to physics. We'll do some of it, but we're not going to do the full section. So we'll do some of the examples. So 7.6, applications to physics. first one is called work. Okay, so work in physics is defined to be force times distance. Force times distance. Okay. So the force is measured in pounds. Pounds or newtons, depending on what system you are. If you are in America, you use pounds. I'm afraid. If you are in the rest of the world, then you use newtons. Okay. And distance is going to be measured in feet. So this is again in the US. And distance is measured in meters everywhere else. So the United States is the only backwards place that doesn't use the metric system, I think. Okay. Okay. So then work is measured in Newton meters. Right. So newtons. No, I should say this one is measured in foot-pounds or Newton meters. Okay, a Newton meter is also called a joule. Joules. Okay, and apparently 1 foot-pound is approximately 1.36 joules. Newton is abbreviated with an N, meters is abbreviated with an M. Pound is abbreviated LB, LBS. Okay, so anyway, so work is defined as force times distance. Okay, so let's just do some examples of how you calculate work. Right, if it's just a constant force and you're moving something through that constant force over a distance, then you just take force times distance. But if the force is variable, one needs to use calculus. Okay, so here's some examples. These examples are just from your book, actually. So you don't have to copy these if you don't want to. Okay. So here's the example, first example from the book. F of x equals x squared plus 2x pounds. Okay, and you move an object from x equals 1 to x equals 3, and this is in feet. And the question is, how much work is done? How much work is done? Okay. So here you have your, you're going from 1 to 3, right? You're going from 1 to 3, and you move this, you have this object, and you move it from 1 to 3, and the force is increasing with time, right? So the force starts out at 0 here, but as you get closer to here, the force is increasing, right? And you're wondering how much work is done. Okay. Okay. So the way you do it is you say, well, if I am here at x, suppose I'm here at x, and I'm going to move a tiny bit dx. Okay, I'm going to move from x to delta x, x plus delta x. I draw bigger. This is x plus delta x. Okay. Moving a small distance there. Okay. Then the work done is going to be the force times the distance, right? So it's going to be x squared plus 2x times the distance. Well, the distance is delta x, right? The force at that point is x squared plus 2x, and the distance is delta x, right? Okay. So the work done is this, right? And so you play the usual game of chopping your distance up into small parts, right? The total work is then, summation is something like x squared plus 2x, x squared plus 2x I, say, delta x from I equals 1 to n. Right? If we chop this thing up into pieces, x1, x2, x3, x4, blah blah blah, through xn. Right. And the total work you can approximate by the force times the small distance. Okay. And then you take the limit. In the limit, we get summation from 0 to 1, from 1 to 3, from 1 to 3, x squared plus 2x dx. Okay? And that you know how to do. It ends up to be some number. Right?